In this video, we're going to simulate an equilibrium system using our Penny Lab. So in our Penny Lab, we had a folder where one side represented the reactants and the right side represented the products. And at any point in time, we said 40% of our reactants are going to convert to products. And at that same time, 30% of our products are going to convert to reactants. Okay, and we'll be able to look at a bunch of different scenarios and see how equilibrium plays out. And hopefully by the end of this video, you have a pretty good understanding of what equilibrium actually is. So for our first data set, actually this should be 0. So our first data set, we started with all our pennies on the reactant side. And at time 0, we would have 100 reactant pennies and 0 product pennies. Then after the first go, our first time interval, we would say that 40% of our reactants have converted to products. So 40% of 100 is 40. And 30% of our 0 products would go to reactants. That would be 0. So we would have a net migration of 40 pennies from the reactant side to the product side. Then after that, the next step, we would have 40% of our 60, so 24 pennies, migrating from the reactant side to the product side, and 30% of 40, which is 12, going from the product to the reactant. So if 24 are moving to products and 12 are going to reactants, now we have a net migration of 12, so we keep doing that. And we keep doing that, and what we'll see is that the change, or the net migration, gets smaller and smaller until you get no net change. And at that point, we have a flat line, and we would say that we have actually reached equilibrium when we have no slope on our lines that represent the amount of product or reactant that we have. So at this point, it doesn't mean the reaction has stopped. It just means that the amount of migration down and the amount of migration up are equal, so you get no net change. Okay? So makes sense. And you can see that the ratio that we get here is we have 57 product pennies and 43 reactant pennies. And when we're describing equilibrium systems, we're going to use a value K, which represents the equilibrium constant. And that is a ratio of our product concentration over our reactant concentration, and that's at equilibrium. So if we calculate that value for the system, we have 57 product pennies and 43 reactant pennies, and that gives us a ratio of 4/3. Interestingly, that is also the ratio that you get when you divide the percent moving to the forward in the forward reaction by percentage in the reactant going to the reactant. So now we didn't start off at equilibrium. We started off at a different set of conditions. Clearly, when you have 100 reactant, 0 product, that was not at equilibrium. So Q is what we're going to use to represent our ratio of product to reactants at any time. So Q was clearly less than K right here. So we ended up making more product to get that ratio where it will be at equilibrium. We'll see that it reaches that every time, okay? So for set B, I asked you to start with 30 product pennies and 30 reactant pennies and 70 product pennies. So at that point, our Q is significantly greater than K. We're at 2.3, and that's way high, or 7/3, and that's way higher than 4/3. So what's got to happen? In this case, some of our product pennies converted to reactant pennies. So our amount of product pennies went down, and our reactant pennies went up until we reestablish that same ratio of 57 product pennies to 43 reactant pennies. So if Q was greater than K, that's going to favor the reverse reaction. You have the amount of products going down, unlike in the first reaction where it was going up. In the third set, I had you start with 35 pennies of reactants, 35 products. So you had the same amount of each. And one of the common misconceptions about equilibrium is that equilibrium means you have the same. People like to just throw the word the same without completing the thought. That's not the case. It's when the reaction stops. So you have the same amount of reactant and product pennies here. So at that point, Q is equal to 1, which is less than K. So if we have a lower product to reactant ratio than will be established at equilibrium, it's going to favor the forward reaction. And we see that as it works its way back to a 40-30 ratio. Right? So establishing equilibrium. Now, once we have that equilibrium established, we can make some changes. And this follows Le Chatelier's principle, where any stress you apply to a system, the system is going to try to alleviate that stress and counter the action done to it to get back to equilibrium. So no matter what the starting situation is, we're always going to get back to that equilibrium constant for a reaction at a given set of conditions, or temperature in particular. So for part B, we took our equilibrium system here of 40 pennies in the product, 30 in the reactant, and we add 10 reactant pennies to it. When you do that, that becomes a ratio of 40 product and 40 reactant. Again, at that point, Q is equal to 1, which is going to be less than K. So we're going to make more product, and we're going to have some of the reactants consumed, and it's going to favor the forward reaction and get back to that same ratio. Even if we don't have the same amount of pennies to work with, we get that same ratio of product to reactant. So if we add reactant, we're tipping the scale out of balance. We're making our Q value, okay, smaller than our K value. So in order to do that, some of the reactants have to convert to products to reestablish that equilibrium. Then I had you guys remove 10 reactants from set C when it's at equilibrium. So instead of having 40 product and 30 reactant, now we took away some reactant. What's going to happen? Well, now our Q value is greater than our K value, so it favors the reverse process. And we see that our amount of products goes down while our reactants goes up, and it again reestablishes that ratio, which is a 1.3 ratio, or 4/3. So big ideas. No matter for a given reaction at a given temperature, you will for an equilibrium system, you'll always get to the same value, that K value for the reaction, regardless of what your starting conditions are or what you do to the chemical system. It's going to work its way back to equilibrium. Now, the two things I didn't do on here that I want you to think about, I manipulated the amount of reactants in here. So now I want you to do on your own, take our equilibrium established after set C, and then instead of adding 10 reactants, add 10 products and see what happens. Instead of removing 10 reactants, remove 10 products and see what happens.